Alright, today we are starting chapter 6 over probability. We're starting with 6.1. We'll also get into 6.2 a little bit. So 6.1 is all about sample spaces and probability. And as you can see, your learning target is to be able to find the sample spaces and probabilities of events. And then you've got your success criteria to determine if we were able to do that. Alright, so sample spaces, just to give you a little introduction. When we're talking about a probability experiment, we're talking about any action or trial that has varying results. So anything that you could do that could have multiple different results. The possible results of these are called outcomes, and a collection of one or more outcomes is an event. The set of all possible outcomes is called a sample space. So an example of these vocab words. A probability experiment, we could say, would be like rolling a six-sided die. The sample space, you could get, when you roll a six-sided die, you could get a 1, 2, 3, 4, 5, or 6. Those are all the possible outcomes. An event, something that has one or more outcomes, rolling an even number because you could get 2, 4, or 6. And then just an outcome would be rolling a 4. Alright, so example 1, we're going to find a sample space. So you flip a coin and you roll a six-sided die. How many possible outcomes are in this sample space? List the possible outcomes. So the first thing we're going to do is we're going to talk about the different sample spaces for each of the different events. So flipping a coin, your sample space there, you can either get heads or tails. Rolling a six-sided die, we already saw the sample space there. You can get 1, 2, 3, 4, 5, or 6. Then we're going to make a tree diagram just to show the possible outcomes. So if you roll the coin first, you can get heads or you can get tails. Once you get that outcome, whether it's heads or tails, then you're going to roll the dice. You can get 1, 2, 3, 4, 5, or 6. You could also get all those outcomes with tails. So 1, 2, 3, 4, 5, or 6. So my possible outcomes, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are 12 possible outcomes. And those are going to be your heads with a 1, heads with a 2, heads 3, heads 4, heads 5, or heads 6. Or you could flip a coin and get tails with a 1, tails 2, tails 3, tails 4, tails 5, or tails 6. Those are all your possible outcomes. Okay? Pause the video for just 2 minutes. I want you to pick either 1 or 2 and do 3. Alright, so now you're back to check. If you chose number 1 and you flip 2 coins, you would get that you could get heads or tails, and from there, you could get heads or tails, which means that you have 4 possible outcomes: heads, 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 tails, tails, heads, or tails, tails. If you chose number 2, you would find that you would get heads or tails on the first coin, heads or tails on the second coin, and then I'm not going to write it out, but you would have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So if I count those tallies, I have 6, 12, 18, 24 possible outcomes. And those are heads, heads 1, heads, heads, 2, heads, heads, 3, heads, heads, 4, heads, heads, 5, heads, heads, 6. Okay, and then the next one, heads, oh no, heads, tails, 1, heads, tails, 2, heads, tails, 3, all the way through heads, tails, 6. Or you could get tails, heads, 1, all the way through 6. And then finally you could get tails, tails, 1 through 6. So that would be your sample space there. Okay, everyone did number 3. So we're making a frequency table. In our frequency table, I've got my marbles, and I've got the frequency in which they occur in the bag. So I've got yellow, blue, and purple. Yellow, I guess I'll use this green color. Got 1, 2, 3, 4. Blue, I got 1, 2, 3. And then purple, I got 1, 2, 3. So this is our frequency table that shows how many marbles of each color are in the bag. All right, the next thing we have, theoretical probabilities. You have definitely seen this before. The probability of an event is going to be between 0 and 1. So in your book, you have this pretty little number line. If the probability is 0, that means there's no chance it's going to happen. And then we can go all the way up to 1, which means that it is certain that it will happen. The outcomes for a specified event are called favorable outcomes. So when we want to find the probability of something, we're finding the probability of the favorable outcome. When all outcomes are equally likely, then the theoretical probability can be found using the following. So number of favorable outcomes over total number of outcomes, and the probability is always written as P of A. So probability of A. So example 2. A student taking a quiz randomly guesses the answers to 4 true or false questions. What is the probability of the student guessing exactly 2 correct answers? So the way we're going to do this is we are going to find our sample space, all the different outcomes that are possible. So we could possibly get 0 correct, which we'll make a table for this one. So if we get 0 correct, that's our easy one. That means I have incorrect, 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 incorrect. All 4 incorrect. I could also get 1 correct, so I could either get the first one correct, the second one correct, the third one correct, or the fourth one correct. I could get 2 correct, so this one will be a little weird. I could get the first 2 correct. I could get the middle 2 correct. The last 2 correct. I could alternate. So I could get incorrect, 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 correct, incorrect, correct. Or I could alternate the other direction. Or I could get the outer 2 correct. Okay, I could also get 3 correct, so I could get the first 3 correct, the last 3 correct. I could get the middle ones as my incorrect, and I don't need a comma there. And then finally, I could get all 4 correct. So these are all my possible outcomes. Okay. What they're asking is the probability of the student guessing exactly 2 correct answers. So that is the favorable outcome. That's what I want to know. So the probability of getting exactly 2 correct. So I'm looking at these outcomes right here. I have 1, 2, 3, 4, 5, 6. That's 6 over my total number of outcomes. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So 16 total. Then what we're going to do, we're going to simplify this. We can write this as a fraction. So simplified, I'll divide both of those by 2 and get 3 over 8. We could also write it as a decimal. 0. So 3 divided by 8 is 0.375. Or we can write it as a percent. So multiply that by 100 or move your decimal place over 2 times. 37.5%. So the probability of the student guessing exactly 2 correct answers is 3/8 or 0.375 or 37.5%. Okay, something else we can look at with probabilities in a sample space is the complement. So if you add all the probabilities together, you're going to get 1 because 100%. You can also find the complement by subtracting 1 minus the probability, and the complement is just everything that is not included in that event. So let's see an example where we actually use the complement instead. So example 3, when 2 6-sided dice are rolled, there are 36 possible outcomes as shown. Find the probability of each of them. So A, the sum is not 6. That is the complement of the probability that the sum is 6. So for part A, I'm going to find the probability that the sum is not 6, I'm going to take 1 minus the probability that the sum is 6. So 1 minus the probability that the sum is 6. So I'm going to find all the chances, all the outcomes where the sum is 6. So 5 plus 1 is 6. 4 plus 2 is 6. 3 plus 3 is 6. 2 plus 4, and 1 plus 5. Those are all 6. So 1, 2, 3, 4, 5 out of my total 36 possible outcomes. So remember with fractions, if I have 1, that's like I have 36 over 36 minus 5 over 36, which is 31 over 36. And then we will find the decimal. 31 divided by 36 is about 0.861. Or 86.1%. Okay, part B. The probability that the sum is less than or equal to 9. That's the complement, so 1 minus the probability that the sum is greater than 9. So I'm going to find all the outcomes where the sum is greater than 9. So I'll start from the bottom since those are the higher numbers. That's 12, 11, 10. We got 11, 10. And then 10. So we have 1, 2, 3, 4, 5, 6. 1 minus 6 over 36. So again, that's like I have 36 over 36 minus 6 over 36. 36 minus 6 is 30 over 36. We'll always simplify our fraction, so we'll divide both of those by 6 and get 5 over 6. Or we can find the decimal, so 5 divided by 6 is 0.83333. So about 0.833 or 83.3%. Okay, so those are complements. We can also use area to find probability, so you're going to have to think back to your geometry formulas. So example 4, you throw a dart at the board shown. Your dart is equally likely to hit any point inside the square board. Are you more likely to get 10 points or 0 points? So we're going to find the probability of 10 points first, which is going to be just in this circle right there. So we're going to find the area of the smallest circle over the total area of the board. So that smallest circle, if you remember area of a circle, that's pi r squared. So the radius of this is 3. So pi times 3 squared over the entire board is a square, right? And so if I want to find the area of the board, I've got 3, 6, 9, 12, 15, 18. So all my sides are 18 inches long. So the area of a square is the side squared, so 18 squared. And then we will simplify and divide. So 3 squared is 9, so I have 9 pi over 18 squared is 324. And then I will simplify that. Let me use a little squiggly equal. So 9 pi over 324. 9 times pi over 324 is about 0.087. Okay. Probability of getting 0 points is going to be your part outside the circle. So we're going to find the area of the square minus the largest circle, and then again over the total area of the board. So I know my bottom is 324. Don't have to do that again. Area of square, again, that's 324. Minus the area of the larger circle. So pi r, that's 369. So pi times 9 squared. So that'll be 324 minus 9 squared is 81 pi over 324. We'll find that as a decimal. 324 minus 81 pi divided by 324. So about 0.215. Okay? So since the probability of getting 0 points is greater than the probability of getting 10 points, that 0.215 is greater than 0.087, you are more likely to get 0 points, then 10. Okay, to save some time for the next self-assessment problems, we're only going to do a few, so we will do 4. We will do 5. And we will do 7. So only do 4, 5, and 7. Pause for about 5 minutes to work on these. All right, number 4. You flip a coin and roll a 6-sided die. So that means that I can get heads or tails, or I can get 1, 2, 3, 4, 5, 6. Hopefully you've noticed that you can multiply those to find your sample space, your number of possible outcomes. So I would find that I can get 12 possible outcomes here for number 4. What is the probability that the coin shows tails and the die shows 4? I know that there's only going to be one possible outcome where that happens. So the probability of that happening, T4, is 1 out of the 12 possible outcomes. Or about 0.083, or 8.3%. Okay, number 5, looking back at example 3, so the probability that the sum is not 11 is going to be the same thing as 1 minus the probability that the sum is 11. So I'm going to count how many of these have a sum of 11. And I'll just use the little laser pointer. So I have right here 1, 2, and that's really it. There's only 2 where the sum is 11. So going back, that's 1 minus 2 over the total was 36. So again, 36 minus 2 is 34 over 36. We will simplify by dividing by 2. You would get 17 over 18. Or we'll find the decimal place, 17 divided by 18, about 0.944. Or 94.4%. All of those are possible answers. All right, and then number 7, in example 4, are you more likely to get 5 points or 0 points? So we're going to find the probability of 5 points. And that is the area of the red circle minus the brown circle in between over the total area, which we already found was 324. So the red circle is going to be pi 6 squared minus the brown circle we already found right here, 9 pi. So 6 squared is 36 minus 9 pi. So 36 minus 9 is 27. And then I'm going to use a calculator. So 27 pi over 324 over 324, about 0.262. Okay, and then we'll find the probability of 0 points, which we already found. Right here, it's 0.215. So, because the probability of 5 points is greater than the probability of 0 points, you are more likely to score 5 points, then 0 points. All right, moving forward. Experimental probabilities. Experimental probability, so everything we've been talking about so far is theoretical. It's in theory. Experimental is based on when you actually do the trials. So it's based on repeated trials of a probability experiment. So now I'm taking what was once theoretical and I'm actually putting it out there into the universe and doing it. The experimental probability, you're just going to find the number of successes, so how many times it actually happened, over the number of times that you did it total. So example 5, each section of the spinner shown has the same area. The spinner is spun 20 times. So before I get into what actually happens, the theoretical probability of any color is going to be 1/4 since they're all the same area. There's a 1/4 chance that I'll hit any color. Experimental is now what we're talking about. So the spinner is spun 20 times. The table shows the results. For which color is the experimental probability of stopping on the color the same as the theoretical? So we're going to find the experimental of all 4 colors. So starting with red, it stopped on red 5 times out of 20. We're going to simplify that down to 1/4 by dividing by 5. And then we'll go on to green. So we landed on green 9 times out of 20. I can't simplify that, so that stays. Blue, we landed on 3 times out of 20. And then yellow, we landed on 3 times out of 20. So the only one that actually matched the theoretical probability is this red here. So red had the same experimental probability as theoretical. The rest were all different. Okay, another example that we can look at for this. Example 6, a research team finds that 368 out of 490 crustaceans have ingested plastic. So in our table, we're looking at the 368 that have ingested plastic. The types of crustaceans that ingested plastic are shown. So we've got shrimp, crayfish, crab, and lobster. The team randomly selects a crustacean that ingested plastic to demonstrate their findings. So they just picked one out of the bunch. What is the probability that they choose a crayfish? So the probability that they choose a crustacean that ingested plastic that is a crayfish. Well, when I look at this, I have 84 crayfish out of the total 368 crustaceans, which I can simplify by dividing by 4. So 84 divided by 4 is 21 over 368 divided by 4 is 92. Or I can find the decimal 21 over 92.228. Or I can say about 22.8%. And then the last little set of notes here. The experimental probability of an event approaches the theoretical probability as the number of trials increases. This is called the law of large numbers. So basically what that is saying is the law of large numbers means that the more and more that you do an experiment, the closer and closer you get to the theoretical probability. So if you only do it a few times, there's a chance that it's going to be way off. If you keep repeating the event or the trial over and over, the more likely you're going to get close to that theoretical probability, like with the spinner we said was 1/4. All right, pause the video, and I want you to do both of these self-assessment problems in about 2 to 3 minutes. I am so sorry. Okay, so first, number 9. In example 5, for which color is the experimental probability of stopping on the color greater than the theoretical? So back to this example. The only probability out of these 4 that is greater than the theoretical is this one right here, green. So that is the answer to number 9. Number 10, in example 6, what is the probability that they randomly select a lobster? So in this one, there are 59 lobsters. So the probability that the crustacean that ingested plastic is a lobster, and I've already forgotten the number, is 59 over the total 368. Which we can make a decimal. 59 over, over 368. About 0.16 or 16%. Okay, so that is it for 6.1. We're going to go ahead and move on to 6.2 because 6.2 is really just a continuation. So in 6.2, we are now introducing two-way tables to represent data and find probabilities. So making a two-way table is just a frequency table that now has 2 different categories attached to your data. So in this example, they give you the frequency table. The 2 categories are the attendance and the class. Each entry in the table is called a joint frequency. So joint frequency, each number in the table. And then the sums of the rows in the columns, so the totals, are called marginal frequencies. Okay, so for example 1, in another survey similar to the one above, 106 juniors and 114 seniors respond. Of those, 42 juniors and 77 seniors plan on attending. Organize these results into a two-way table, and then find and interpret the marginal frequencies. So again, we've got the same type of data here. We've got organized by class, juniors, and seniors. And then we've got organized by attendance, attending or not attending. So 106 juniors respond, which means that the total, we're going to come out here, the total number of juniors is 106. 114 seniors, so total of 114 seniors. Of those, 42 juniors and 77 seniors plan on attending. All right, so now we need to find what is missing. So not attending. If I have 106 total juniors and 42 are attending, I'm going to take 106 minus 42 to find how many are not attending. So 64 juniors are not attending. If I have 114 seniors and 77 are attending, I'm going to take 114 minus 77 to find that 37 seniors are not attending. Then I'm going to find all my totals. So for attending, I have 42 plus 77. It's 119. For not attending, I have 64 plus 37. 101. And then my combined total, you can either add the column or the row for total, it doesn't matter. We'll just do 119 plus 101. If you add them both, they should both equal the same number though. So if I were to go back and add 106 plus 114, that should also equal 220. Okay, so this is my two-way table. My marginal frequencies are these numbers on the outside. So I'll use a different color to show that. So this marginal frequency goes with my juniors. So this means that 106 juniors responded. This total goes with my seniors, so it means that 114 seniors responded. This is my full total, so it means that 220 juniors and seniors responded. Then these totals over here, this one is in my not attending column, so 101 students are not attending. And then finally, this one is my attending column, so 119 students are attending. All right, and if you want to pause on this screen so people can finish writing, I'm sure I wrote a little quickly, but that is your two-way table and your marginal frequencies. All right, self-assessment. Take about 4 minutes to make your own two-way table and interpret the marginal frequencies. Okay, for this problem, you should have split your two-way table into the two categories of gender so boy and girl, and their opinion on planting a garden. So in favor or against. So of 96 boys, so 96 total boys, 61 are in favor. Of 88 girls, 17 are against. So I'm going to fill that in. So I'm going to find boys by taking 96 minus 61. I'm finding 35. Boys are against. And then girls, 88 minus 17. So 71 girls are in favor. And then find my totals for in favor and against. So in favor, 61 plus 71 is 132. 35 plus 17 is 52. And then I'll add 132 plus 52. So that is 184. And then we will interpret our marginal frequencies. So you would have found that 132 students in favor. 52 students are against. 184 students responded. "88 girls responded, and 96 boys responded." If you flip-flopped it, so you put your gender as your rows and you're planting a garden as your columns, that's fine too, as long as this all matches the interpretation. Okay? The next thing we can do with two-way tables is we can find what's called relative and conditional relative frequencies. A joint relative frequency is the ratio of the joint frequency to the total number of values or observations. So you're basically just taking the frequency that you found in the table divided by the total. The marginal is just the sum of the joint relative frequencies. So same as before. Once you find the joint relative frequencies, the marginals are just the sums. So for example 2, we're using the data from example 1 to make a two-way table that shows the joint and marginal relative frequencies. So with these two-way tables, again, same organization. So in example 1, we were organized by attendance, and class, so what we're going to do, I'm going to go back to example 1. And so I had, in this first box, 42 juniors attending out of 220. So 42 out of 220. And I'm going to find the decimal place for that. So 42 out of 220 is about 0.191. Now, I drew my table a little tiny, but it's okay. All right, for juniors not attending, I had 64 out of 220. Which is the decimal, about 0.291. For seniors attending, I had 77 out of 220. So that decimal is 0.35. And then for seniors not attending, that was 37 out of 220. Which is about 0.168. For totals, I'm going to add, so 0.191 plus 0.291. Is 0.482. 0.35 plus 0.168 is 0.518. And then my columns, 0.191 plus 0.35 is 0.541. Not attending, 0.291 plus 0.168 is 0.459. And then add, we'll just do the last ones, 0.541 plus 0.459 is 1. Make a note here. This will always be 1. because you're adding all the probabilities. Okay, and then interpret one of the joint relative frequencies and one of the marginal relative frequencies. So one of the joint relative frequencies, I'll use pink. We'll just do this first one. So the joint relative frequency, JRF, 0.191. That means that about 19.1% of those surveyed are juniors who are attending the concert. This also means that the probability of selecting a random student that's a junior that's attending the concert is 19.1%, which you can see in your book. And then let's pick one of the marginal relative frequencies. So one of my numbers on the outside, we'll go with this one. I shouldn't have done green, but that's okay. The marginal relative frequency, 0.459, means that about 45.9% of those surveyed are students that are not attending the concert. Because we're looking in this column right here. All right, for the self-assessment, don't do number 3, I just want you to do number 2. So pause the video and take about 5 minutes to do number 2. All right, so number 2, we would set up our table just like we used in exercise 1 from the self-assessment. So by gender, and by if they're in favor or against. Of planting the garden. Okay. So you would have divided, for boys in favor, 61 divided by 184, and got 0.332. For girls in favor, you would have divided 71 by 184 and gotten 0.190. For boys against, you would have divided 35 by 184. Oh, I am doing this wrong. Forgive me. I hope you guys were yelling at the screen. Okay, boys in favor, 61 divided by 184. No, that one was right. 0.332 was right there. Girls in favor was wrong. That should have been 0.386. For boys against, you should have gotten 0.190. And for girls against, you should have gotten 0.092. For your totals, so in favor, would be 0.718. Against would be 0.282. Boys would be 0.522, and girls would be 0.478. This total is always 1. And then you would have picked any of the different answers or any of the different numbers to interpret. So you may have said that 0.332 means that about 33.2% of the students surveyed are boys in favor of planting the garden. You could have possibly said that 0.282 means that 28.2% of the students surveyed are against planting the garden. But just check and make sure that it matches what column and what row it's in. All right, next, conditional relative frequencies. So a conditional relative frequency is the ratio of a joint relative frequency to the marginal relative frequency. You can find a conditional relative frequency using a row total or a column total of a two-way table. So, for example 3, use the survey results in example 1. Make a two-way table that shows the conditional relative frequencies based on A, the row totals, and B, the column totals. Interpret one of the conditional relative frequencies in each table. So we'll start with A, the row totals. Again, we're setting it up the same way. We have attendance, so we have attending, not attending. Oh, we don't need total for this one. Don't copy me. And then we have class, juniors, and seniors. And that does kind of look like the check mark, so let's fix that. All right, so what we're going to do to fill in these tables, I'm going to go back to example 2, and I'm using my marginal relative frequencies. So juniors attending, that's 0.191, and I'm using my row totals right here. So 0.191 divided by 0.482. And I'm going to make more room because that's not going to work. Okay, 0.191 divided by 0.482 is about 0.396. Okay, juniors not attending, that's 0.291 divided by that same row total. .482. So about 0.604. All right, seniors attending, that's 0.35 divided by my row total, 0.518. So about 0.676. And then finally, seniors not attending, 0.168 divided by 0.518. So about 0.324. Okay, and then we can just interpret one of these conditional relative frequencies. So I'll pick, I don't know, your book picked 0.604, so we'll do 0.676. So the conditional relative frequency, 0.676, means that about 67.6% of the seniors surveyed are attending the concert. Since I'm looking at row totals, so this number is the percent of these seniors attending the concert. All right, part B, column totals. So now we're looking at attendance rather than class. Still same setup. You have attending and not attending. I don't know why I drew that line so long. And then we have juniors and seniors. So now I'm taking the same numbers. So I'm going to go ahead and copy those over. 0.191, 0.35, 0.291, and 0.168. And now I'm putting those over my column totals instead. So looking back here, my attending is 0.541. So I'm putting my attending over 0.541. And then my not attending is over 0.459. So not attending is going over 0.459. And then for this one, I'm going to cheat and use the book, but we would use our calculator. So that's 0.353, 0.647, 0.634, and 0.366. And again, I'm just going to choose one at random. Since your book did 0.634, I'll do a different one. We'll do this one. So the conditional relative frequency, 0.366, I'll add a 0 there, means that about 36.6% of, and now we're talking about column totals, so of the students not attending, are, and then we look at the row, so are seniors. All right, for the self-assessment, instead of making you make your own two-way table, we will just skip number 4. But I do want you to pause and take about 2 minutes to do number 5. All right, so we're checking. Number 5, use the relative frequencies in example 2 or 3 to find the probability that a randomly selected student from the survey is a senior who is attending the concert. So examples 2 or 3. Look in here or here. Trying to find the probability that a randomly selected student from the survey is a senior who is attending the concert. So we'll just look here. Senior attending the concert. Looking at example 2, because that's going to tell us the probability, is right there, 0.35 or 35%. The one reason I would not use example 3, so use example 2. The one reason I would not use example 3 is because this is telling you given, like it's saying this is the probability that you have a senior given that they are attending. This is the probability or just kidding, backwards. This is the probability that you have a senior given they're attending. This is the probability that you have a student that's attending given they're a senior. This one takes into account just a senior who is attending the concert. You don't have any kind of given there. Okay, so that is it for 6.1 and 6.2.